distinguished speakers. We have a special two-chairman session. So I will. So now we will have the infinite pleasure of having Felipe Rosso, who is going to talk about solving puzzles in deformed Jackiw-gravity, phase transitions, and non-perturbative effects. So, Felipe.
Thank you, Gaston. Let me share my screen here. Good. So, the usual thing, thank you for the organizers for putting this very interesting meeting together. I'm very happy to be here talking about this work, and hopefully you get something out of it. So as Gaston already said, I'll be discussing this recent paper, and this is in collaboration with Clifford Johnson. Okay, this is the archive number if you're interested. And before doing anything and showing you anything, let me tell you what's the main motivation and result of the paper. So the idea is that there were two papers that came out this year that were very interesting, one by Turiachi and Maxfield, and the other one by Witten. And the main result of those papers was that they were able to show that some deformations of Jackiw-gravity are described by a random matrix model. And they're very nice papers, and the result is actually very strong. But there was a puzzle noticed in those papers that was left unresolved. There was a problem for some particular deformations. And the objective of our paper with Clifford was to understand that puzzle and actually to solve it. And we did just that for a class of deformations. We showed that the puzzle that arises in the Witten paper is solved. And the way it is solved is by properly accounting for a phase transition. Okay. So what I will be trying to do in the rest of the talk is to try to convince you, to introduce the problem and to convince you that this is the right solution, that the proper way to account for this issue is to recognize this interesting phase transition. Good. So in order to begin, let me start by having a quick review on Jackiw-gravity, okay? Since the tools we use will be very clear in this simpler context. So what is Jackiw-gravity? Okay, Jackiw-gravity is a two-dimensional theory, okay, that has the action that you see over here. And it's, as I said, it's two-dimensional, and there are two degrees of freedom, well, not 2 degrees of freedom, but there are two fields that you have to take care of. One is the metric, okay? And the other one is a dilaton, okay, a scalar field. And the action is what you see over here. We have first term, okay, and this first term is actually quite important, that it is composed first of this constant S0, S0, okay, that is simply a parameter of the theory. And we will be mainly considering the case in which this parameter is large. Okay, and this parameter is accompanied by this other thing, that's the Euler characteristic, that basically measures the genus of the manifold in which you are placing the theory on. Okay, so this is a topological term, and then you have this other term, okay, the second term that we see over here, that it is the bulk term, and as you can see, it's very simple. What we have is we have the dilaton appear linearly. And then we have the Ricci scalar appearing in perhaps the usual way. And the reason the theory is so simple is because the equations of motions are actually extremely simple. When you do the variation of this, the dilaton field acts as a Lagrange multiplier. And what you end up getting is that the solutions of the theory are only given by the metrics that have Ricci scalar equals to -2. Since this is a two-dimensional theory, this completely fixes the metric to be hyperbolic metrics. This is to say Euclidean ADS2, okay? So this is a very simple theory. And that's the reason it has attracted a lot of interest. Because although the theory classically is quite simple, quantum mechanically, it's quite interesting, and we can actually solve it completely. So in order to consider the quantum theory, what we do is we consider the partition function, okay? So in order to compute a partition function, we have to say, okay, what are the boundary conditions that you impose? And the boundary conditions that we impose are the usual thing that we do in ADS, where we take well, Poincare coordinates, let's say, or yeah, whatever, and we take the boundary to infinity, okay? And the boundary conditions are ultimately determined by the renormalized length of this boundary. Although the boundary goes to infinity, we can make sense of a renormalized length. And then the way in which we construct the partition function is what one would naively do. This is to say, we do the path integral over all configurations of the dilaton field and the metric. And we have the action in the usual way. And the nice thing is that this partition function organizes itself in a topological expansion. And let me tell you what I mean by that. What I mean is the following. This first term that we have over here, that schematically I have drawn a disk, okay? This is a contribution that comes from solving this path integral when the manifold that you're considering has a disk topology, okay? And the important thing to notice is that due to this topological term that we have over here, the contribution coming from the disk topology comes weighted by this factor over here, e to the s naught, okay? As I already said, S naught is supposed to be a large parameter, okay? So this will be the dominant contribution to the path. But then you can say, okay, what if I should in principle consider all geometries that fill out the disk? And that is true. So then you say, okay, I should consider this other contribution. But what I'm doing now, I'm adding some interesting structure, okay? I'm considering some handle over here. And as a consequence of this, given that we have this Euler characteristic over here, the weight that comes associated to this contribution is different, and it is given by e to the minus s naught. This is to say, since s naught is very large, it's very small, okay? And in principle, you can continue by considering more complicated geometries, okay? And this is what I mean when I say a topological expansion.
So a question. So for some reason, you play the game in such a way that you will have only one boundary, because otherwise you also will have other kind of topology, and it's just the setup is like that.
Yeah, you can play the other, and actually in the paper where this was actually worked for the first time by Shaker and Stanford, they played the game with arbitrary numbers of boundaries, and it's a very interesting question. I'm introducing the case with a single boundary because it's simpler to pedagogical, but you can play the same game with whatever number of boundaries you want. Good. So, well, as I was saying, this theory was actually solved. It was solved in this extremely nice paper from last year by Shaker and Stanford. And what they were able to show, that the computation, this topological expansion of the partition function in Jackiw-gravity, it is actually the same. And when I say the same, is that you can compare each of these terms in the contribution. And what you find is that they can be, you can also reproduce those computations by a Hermitian random matrix model. Okay, so I will tell you what a Hermitian random matrix model is in a couple of slides. But let me just say that what you have, the observables are given by matrices, and you have to do an average ensemble of over matrices. And you see that the partition function in Jackiw-gravity, this gravitational observable, is given by this quantity. We have a trace. The trace is a trace over matrices, nothing weird going on. We have the beta appearing over there, and M, that it's a matrix. And this was shown in this very nice paper. And the way in which this was shown was by matching each of the terms to all orders in the genus expansion. This is to say, for each of these terms. Good? And to give you a flavor of how this works, let me tell you that the way in which this works is by first computing this partition function. Okay. Luckily, this can be computed exactly. This is to say, we're doing a quantum computation here, and the nice thing is that this partition function is one loop exact. This is to say, you do not have to go beyond 2 loops, because all 2 loops, 3 loops, they all vanish. Okay. So once you have the dispartition function, the structure of the theory is so rigid that all the other higher order contributions are already fixed by a recursion relation. Okay, so if you have the first one, you can compute the second one with a recursion relation, and the third one, and so on and so on. And in this paper, yes.
Can I ask a question? You're doing this matching is order by order. Is there any possibility of a non-perturbative thing that's different?
Yes, that is an excellent question. Yes. And that is something that from the gravity perspective, it's quite difficult to address. Because notice that from the gravity perspective, it's a doubly non-perturbative corrections. In the sense that you would say that, to cut it short, from the gravity perspective, it's quite difficult to address it, but from the matrix model perspective, you can do it. And that is actually one of the things we did in this paper. But I will not have time to discuss it. But
I mean, is there any possibility that they don't match at the non-perturbative level? Or?
Yes. The problem is that you can't, I don't know of anyone who knows how to compute the non-perturbative contributions from the gravity side.
Okay, great. Thanks.
From the matrix model side, you can compute them. You can get plots, and if I have time, I will show you a couple of numerical plots. But from the gravity side, you don't know how to compute them. Good. So this is the way the story works. And let me just tell you that I will be, instead of working with the actual partition function, it will be convenient for me to work with the spectral density. Okay, that is simply defined through a Laplace transform in this simple way.
Felipe, hi. How are you?
Yes.
What's the expansion parameter in the random matrix side?
Yeah, that's an excellent question. So one thing I haven't told you, and I will tell you in a moment, is that the Hermitian matrix model is evaluated in a particular limit that's called double scaling limit. And in that context, there's a parameter that controls the double scaling, and that is the parameter that we will match with this parameter e to the s naught that appears on the gravity side.
So the matching is order by order. Then I mean, Nico, question, I didn't get the answer to that.
Yeah, the matching is order by order. Non-perturbative effects, we don't know what can happen. Good. So this is very interesting. This is a very interesting theory, and the natural question is, can this be generalized? Okay, and the idea is, can we generalize this to other two-dimensional dilaton gravity theories? And the answer is yes. And this goes back to the papers I was referring to by Maxwell and Turiachi and by Witten earlier this year. And the idea is that the deformations they consider in those papers have the action that you see over here. First, we have the usual Jackiw-gravity stuff I just told you about, and then you have this additional contribution, okay? That is basically adding a deformation of the potential of the dilaton field. And the deformation is given by this function that we see over here, that is an insertion of exponentials weighted by two parameters, lambda and alpha. Okay? So it's some deformation. And the very nice thing they found in those papers is that the story also holds true for these deformations. This is to say, it's dual to matrix model, and you have the topological expansion and the matching to all orders. It's perturbative, of course. What is the difference? The difference is that the disk partition function or the disk spectral density are different for Jackiw-gravity and for these deformations of Jackiw-gravity. Therefore, you have the same recursion relation, but their starting point is different.
Sorry, but relation to the question I made before about the boundaries, wouldn't be this effectively as adding boundaries, because it's like adding punctures in the space with a weight alpha or something like that?
Good. So the reason they consider this particular deformation is related to what you're saying, in the sense that adding these deformations is actually the same as adding defects to the surfaces. So the way in which they are able to solve it is by interpreting these punctures that you see over here as defect insertions. And that's the way in which they are able to perform the sum. It is true that by analytically continue over this parameter alpha, the defect can be turned into another boundary. But yes, I don't know if I answer.
Felipe, one more in this line.
Yes.
So these
yes.
defects in order to be introduced, they have to be introduced with this e to the phi form. I cannot choose any other functional form. Is that the case?
Yes, that is the case. And there are some additional constraints on the range of these angles alpha. In the original paper, alpha has to go between 0 and 1/2. Then Turiachi, with some collaborators, was able to extend this to a larger range, 0 to 1.
Okay, thank you.
Good. So now let me tell you what's the puzzle that was already noted in these papers. And the puzzle is that when you compute the spectral density given by the disk partition function, remember that this is a function of these parameters, lambda and alpha. They found that for some choices of these parameters, the spectral density becomes negative, okay? And schematically, what you find is something like this, okay? And this is quite problematic because, as I've been telling you, the way in which you determine the whole topological expansion is by you start from the disk and then you use the recursion relations, okay? So if the disk result that you get is already sick, okay? It has this negative thing that we do not know how to make sense of it. The whole topological expansion is sick, okay? So there are two questions that we wanted to address. What is the origin of the issue and whether this can be fixed? And what we found in our paper is that the origin has to do with some multi-valued potential that appears on the matrix model. And the way it is naturally fixed by the matrix model is by accounting for a first order phase transition that actually shifts the vacuum energy, okay? So that's what happened from the matrix model perspective. I should say that all of our computations are using the matrix model stuff, okay? A very interesting question is to understand how this can be properly understood just from gravity side. And one more thing I should say, this particular issue for the particular deformations we will be considering is an issue that appears in the Witten paper. In the Turiachi and Maxfield paper, this is not actually an issue, okay? But from the Witten paper, it wasn't clear how to actually solve it. Okay. So let me tell you the outline, okay? First, what I will do, I will introduce this for a particular deformation, okay? I will see explicitly how it is that it turns negative. Section 2 is the main section, and this is, in this section, what I will have to do is I will have to introduce the matrix model technology that we use to solve the problem. And this is old stuff from the early 90s, okay? And I apologize in advance because I will have to throw stuff to you because I will not have time to introduce everything, and hopefully you will be able to at least follow the whole story. And in the third section, I will show how the phase transition arises from multi-value potential. All of this, of course, is if we have enough time, which I am not entirely sure. Good. So this is the particular deformation I'll be considering, okay? I choose a particular combination of exponentials, okay? The dispartition function was computed by Witten, and it has this functional, it's a very simple functional form over here, okay? And the negativity is quite easy to see, and you see by expanding to first order in energy. And you see that when lambda is larger than this lambda critical over here, this first contribution becomes negative, therefore the spectral density becomes negative, and we are doomed in some sense. So the question is, let's consider this particular theory and see how we can solve or understand this issue from the matrix model perspective. Good, so let me introduce what a random matrix model is. So we start from a matrix M, that it is Hermitian of some dimension n. The observables of the theory are stuff that you build out of this matrix. For instance, this observable is quite important because it will be dual to the partition function of the JT gravity theory. And another quantity that we have that is also important is the spectral density, that from the matrix model perspective is simply insertions of Dirac delta at the eigenvalues Si of the matrix M. The way in which you compute observables is given over here, okay? You basically integrate over all matrices, insert the operator that you're interested in, and you consider this weight function, okay? That it is determined by a potential V, okay? So this potential is, you can think of it as the quantity that defines the matrix model. you can think of, usually you can think of it as a polynomial, but it can be something more complicated. Good. And so one very powerful method of solving this theory that is actually completely solvable is called the method of orthogonal polynomials. Okay. And the main object in this formalism are some polynomials that I noted here, Pn of S. And the idea is that these are orthogonal polynomials with respect to the measure that you get from the matrix model. Notice that here we have ds, okay? That's the potential that defines the matrix model. Okay? So the nice thing of this formalism is that if you consider this set of orthogonal polynomials, you can actually compute any observable you're interested in, okay? They're all determined by these polynomials. And note that these polynomials effectively build a Hilbert space, Hn, dimension n, okay? So that you have some states that you can label by this ket n, okay? That effectively define, not define, allow you to compute whatever observable you're interested in the matrix. Okay? Again, there's a lot of interesting structure, and I haven't told you exactly how to do this, but this is something that has been well known to people who study these models. And as I already mentioned in regards to Alan's question, the particular matrix model that is relevant for Jackiw-gravity and for the deformations of Jackiw-gravity is a matrix model in what is called the double scaling limit. Okay, this is a procedure that you apply to a matrix model that was developed in the early 90s. And the idea is the following. The idea is that you take n to infinity. Remember, n is the size of the matrix. So we're considering very large matrices. And then we tune this potential, V of m, to a critical potential, okay? Where the criticality is defined in some particular way in which the free energy diverges. Derivatives of the free energy. So this is a particular limit that you can take of the theory that is quite interesting. And let me tell you what happens to the quantities in the ordinary matrix models when you take this double scaling limit. So Felipe, as I was, yes.
Unless you are a friend of the chairman, you have 5 minutes.
Yeah, I'm screwed. Yeah, so let me keep on. I will not be able to tell you everything, but I will tell you when we're done. So the idea is that you have the observables that under the double scaling limit, they get mapped in this particular way. The Hilbert space formed by the orthogonal polynomials is no longer discrete, but now it's a continuum. So now your observables are actually differential operators, okay? So, yeah. So the way in which you compute now observables...
You have 15, okay, you have 15.
Ah, okay. Okay, good. So maybe
so the chairman is not your friend.
Makes sense. So the idea is that in this double scaling limit, these orthogonal polynomials become an infinite dimensional Hilbert space. Okay, that is basically a quantum mechanical system. Okay, so the idea is that now the orthogonal polynomials are this x, where x is a continuous parameter, and here I'm giving you a formula for how it is actually that you compute this observable that we are interested in. Okay, so what we see over here is we have an integral over x, and then we have the diagonal component of this differential operator. Here we have this h bar, okay? And this h bar is the expansion parameter that controls the double scaling limit, okay? And looking ahead, this will be the parameter that will be related to the topological parameter in the expansion of Jackiw-gravity that Alan was asking about. And then you have this central quantity that this is the potential U of x. Let me stress that this is a different potential from the potential V of m that I told you about a couple of slides ago. Okay, this is a potential that arises that determines the particular model you're working with. And
sorry,
yes.
Sorry to interrupt. I know you don't have much time, but h bar is basically n.
No, it's more complicated than that. It's when you take the double scaling limits, you have to take the limit in a very smart way. Okay, So H ends up being related to N, but also to another parameter delta that you have to introduce.
Okay, but was it originally in the matrix model, that other parameter?
No, it's not N. It's not 1 over N in the original matrix model. It's something more complicated than that. I am hiding a lot of stuff under the rug that I'm not telling you about regarding how it is that you actually take the double scaling limit. There are some very nice reviews by Ginsparg and Moore and some other people that I encourage to read. They are very nice.
Good, thanks.
Good. So this central quantity is this potential U, and you might ask, okay, how are different double scale matrix more related? Okay, they're related through different U's, okay? And the way U is determined is by something that's called string equation, that it is nothing more than a differential equation, okay? It's a differential equation that's satisfied by this potential U of X. And here I wrote a couple of examples, okay, of what this string equation can look like. Good. So I'm pretty sure I might have lost a lot of you because I've introduced a lot of technology and I haven't told you exactly how to get it. So let me try to save those of you who have not followed this, and let me give you a recipe for computing stuff. So the idea of this matrix model technology is the following. The first thing you do is you choose these coefficients, Tk, okay? Taking a particular set of coefficients will give you one theory. If you change them, you get another theory, okay? And these coefficients Tk determine this string equation that you see over here that ultimately determine the function U of X, okay? Once you solve this differential equation and you get the function U of X, you can use this expression over here, that this on the right-hand side, all we have is a trace in quantum mechanics, okay? There's nothing mysterious about it. It's a potential, so it's nothing weird. And then once you're able to compute this trace, the matching with gravity comes as given by this box. This is to say, the topological expansion in the gravitational side in e to the minus s naught is equivalent to the perturbative expansion in h bar of this observable, okay? Good. So now let us analyze the analogous of the disk partition function. In the disk partition function from the gravity side, it was the leading genus contribution. Using this technology, from this perspective, it corresponds to the h bar going to 0 contribution. That this potential U of X that will play a crucial role, I will note in this limit as U0 of X. And the string equation in this limit becomes this constraint over here. Note that this is nothing more than an algebraic constraint. All we have is U0 to some power, okay, in this infinite series. And the spectral density is computed by this equation over here. This technology was applied to Jackiw-Gravity last year in these two papers, okay, by Johnson and Hell.
Felipe,
Yes.
just a small question. This quantum mechanical model, is it really in some sense the boundary theory? I mean, can you give a physical meaning to this potential? Or is it just an auxiliary computational technique?
Yeah, that's an excellent question. I do not have a compelling answer for. There have been attempts to actually consider it as some kind of dual theory that is an actual theory, but to be safe, I will simply be considering as an effective description that you get from the matrix model perspective. It is an excellent question to investigate that more. Good.
Okay,
Good. So now let's go back to the form Jackiw-Gravity, that theory that we considered a couple of slides ago. And what we do is the following: using the spectral density, the disk result computed in as computed in Witten paper. What we can do is we can go back and see what are the coefficients decay and the actual string equation that you get for this particular theory. And what you get is this equation, okay? What we have over here is an algebraic constraint, okay? Notice that U0 appears all over the place, but there is no derivatives of U0. And this is the algebraic constraint that determines the potential. This is the leading genus potential, okay? So what we want to do is to analyze what happens to this implicit definition of this potential that we're working with for the different values of lambda, alpha 1, and alpha 2, where lambda, alpha 1, and alpha 2 determine the particular deformation of JT gravity that you're considering. In order to do that, remember, as this is an algebraic constraint, what we can go back to is to the implicit function theorem, okay, very basic stuff. And that tells you that this function, u0 as a function of x, okay, will be defined over the whole real line if and only if the derivative of this g0 that determines the leading gene string equation does not vanish. And so all you have to do is take this function, okay, that we have over here, this g0, compute its derivative, see if it's vanished, and sadly, it always vanishes, okay? Even for JT gravity. If you consider JT gravity, what you find is that this is never satisfied, okay? So when you get to this, you say, oh, I mean, we're done, right? Because even the simplest case of JT gravity, it seems to be suggesting that this function will not be defined over the whole real line. But then we go back and note the following. Note that the observable that we're actually interested in, and actually all observables, they are actually determined by an integral, not over the whole real line, but over half of it. This is to say for x negative. This means that maybe, just maybe, we are able to define this function u of x from the algebraic constraint coming from the string equation in the half real line, in the negative x line. If we are able to do so, then we can compute this thing and match with the gravitational result. And this is like we should, right? Because Stanford already showed that this should be true, so this has to be true. And I will show you some plots in a moment. Let me just, before doing that, tell you this once again. The value of this potential at the origin gives you the vacuum energy, okay? And this will be important because the vacuum energy is what we will actually be following when wanting to recognize a phase transition and so on, okay? So let us start by considering the simplest case of pure JT gravity, no deformation, and see what happens with the definition of this function u0. This is what we find when we combine, okay? In the simplest case, this function g0 is given by this Bessel function, okay, and x. And what you can do is you can simply plot this in a computer and you rotate the thing to compute the inverse, and you find the plot that you see over this side. Notice that this is the origin, this is x equals 0, okay? And we have all these oscillations coming from the Bessel function, okay? And in all this region, the function u0 of x is multi-value, okay? But if we only consider, there is a single branch of the solution that we can consider that is single valued and well-defined for all x negative. So this is the unique branch we can consider for the implicit definition of the function that will actually give us the perturbative expansion of JT gravity. And this is something you can do. You can take this branch and start computing perturbative corrections, and you find that everything matches to the gravity side. And an important thing to note is that the function u0 vanishes at the origin, okay? And this is nothing more than the statement that the vacuum energy, the threshold energy for pure JT gravity is equal to 0, okay? So hopefully we now understand the case of JT gravity. So now let us start turning on the deformation. This means going away from lambda equal to 0 and see what happens. So let us consider lambda in this range, okay? Lambda between 0 and smaller than the lambda critical. The constraint that we get in this case is a little bit more complicated, okay? Because we have this additional contribution, okay? But if you plot this function, what you get is a very similar story. Notice that even though the curve changed, the overall features are the same, okay? This is to say the vacuum energy is 0 because u0 vanishes at the origin, and we have this single branch that determines all perturbative physics. What you can do is you can compute the spectral density in this case, and you find that the equation, the result you get agrees with the Witten result. So now we're ready to go further, okay? We can continue this into the region in which we know the Witten computation fails. This is to say for lambda larger than lambda c. And we already see that there's an additional and interesting structure already developing, because now there is something interesting and that is different from the other case. Now we note that the curve has this interesting bend over this region, okay? So there are two things we can do. We can first say, okay, let's define the function, or let's take the branch that starts at the origin. This is to say that has vacuum energy equal to 0, and we follow this thing, okay? The first thing we see is that in this region over here, the function is multivalued, okay? And if you do this naively, what you end up getting is you end up getting the Witten result. This is to say the spectral density that is negative in this region. And this is because we have started from the origin, and then we are considering this contribution of the curve that is multivalued. But from this perspective, it is very clear that the right thing to do is not to start from the origin, but start from this higher point, okay? That effectively it corresponds to having some non-zero vacuum energy, okay? Because the function u0 no longer vanishes at the origin, but has this positive value. And then we include this contribution. We define the function in this way, okay? And the next thing is that if you do this, you end up getting a positive definite spectral density. And moreover, the result that you get for the spectral density agrees with the result, not from the Witten paper, but from the Maxwell and Turiachi paper, okay? So it solves the issue. This is my last slide. So summarize. For lambda smaller than lambda c, we have that this function u0 at the origin vanishes. The spectral density is computed from this very general formula that is explicitly positive. And you can compute the integral and you get the Witten result, okay? Now for lambda larger than lambda c, you have that the value of the potential at the origin is no longer 0, okay? It's given by this non-trivial value. And the spectral density is again given by this thing, but now the integral is explicitly positive, okay? And the difference comes from the fact of this lower endpoint on the integral. If you plot the vacuum energy as a function of lambda, you get this schematic plot over here, and you can characterize the phase transition and so on. I mean, you can characterize several aspects. You see that the phase transition is first order, and yeah. So this is the way in which you can solve the problem. Again, note that this is all coming from the matrix model side. And since I am out of time, I will not tell you anything else. Let me just finish with a couple of plots, okay, of other stuff in the paper. These are numerical plots for the potential, okay. Let me stress that this is not perturbative, okay. What you can do is you can consider the problem non-perturbatively. In that case, you cannot do analytics, but you can do numerics. And you can compute the potential for these deformed JT gravities, and you get potentials that look like this. And from this, you can compute the spectral densities, and you get some numerical results that look like this, okay? Here you can see the way in which the vacuum energy starts to change, okay, as you increase lambda, okay? Yes, so this was just to show you some things, but I don't have enough time to tell you about it. So thank you, I'm done.
Okay, thank you, Felipe, for the talk. We have two questions. The first one by the Marquis of Viña del Mar, also known as Ana Balón. So please, Andres.
Thank you, Gaston. Thank you, Felipe, for the very nice talk. I just want to mention, well, first a question is that in general, when you compute the vacuum energy with ADS-CFT, you get a negative result, right? The vacuum energy is negative because what you are computing is the Casimir energy of the dual CFT. In this case, I think this is the first case that I see that the result is positive, which is still is very interesting, right? So it's just a remark, this is not a question. But my question is more about that since you have this very nice model that you can solve, so you have quantum gravity, let's say well-defined, and so there are several questions that you want to know from higher dimensions about quantum gravity. One of the questions that typically people pose about quantum gravity is that the vacuum expectation values of fields on the vacuum of the theory is equal to 0. Let's say you have a scalar field and you evaluate the vacuum expectation value in a theory without spontaneous symmetry breaking is equal to 0. So what is the vacuum of this quantum gravity theory, and what is the vacuum expectation value of the metric in the vacuum of this theory?
Yes, so those are good questions. Let me start by saying that I don't think of this vacuum energy as the same vacuum energy that you get from usual ADS-CFT when you do like the calculation that you're referring to, the Casimir energy. That I don't think, it's not obvious to me that they are the same thing. Basically because in this case, the ADS-CFT duality that you get, it's a different one in the sense that the bulk gravitational theory is not dual to a single theory, but it's dual to an ensemble of theories. You're doing an ensemble average. So I'm not sure they are the same, but maybe they are, I don't know. And then your other question. Yeah, so your other question, I'm not sure how to answer it, but what I have to say is that note that in this case, we're considering pure gravity. So there are not actual fields that we can insert and compute expectation value. That's actually a very interesting question. How is this story modified when I'm not only considering JT gravity, but I put a scalar field, an additional scalar field of fermion, and I start computing expectation values. So in this case, I wouldn't know. Yeah, that's all I have to say for that question.
I don't really see why you cannot compute the vacuum expectation value of the metric. It's just you put the metric in your integral and you integrate, you know?
You're saying, just so to make sure I understand the question, you're saying that we take this path integral that we see over here,
and you insert the metric.
We insert the metric. Yeah, I have no idea if something like that is possible. From the, yeah, I don't know. It's a good question.
That would be an interesting thing to do, I think. Because like, if you read the literature of quantum gravity, they always wonder about these kind of things in higher dimensions. So now that you can actually do it, you maybe can try.
Yeah, I'm guessing, I've never thought of this. One thing I can think of is if you insert the metric, you have to do something with the coordinates, right? You have to contract them in some smart way so that the end result does not depend, is coordinate independent, right?
Yeah, well, yeah. You need to fix the gauge in a certain way.
Yes, but
okay, thank you very
honestly,
much.
I don't know, but it's a good question.
Thank you very much for your answers.
Okay, I thought Alan had a raised hand, but now I don't see him. So, Alan, you have a question? Alan Rios.
No, I think it was the clapping.
Okay.
Yes, I was clapping, sorry.
And okay, Alan Garbars? No. So, Nico Gowensky.
Hey, so thanks for the talk. Maybe you said it at the end and I missed it, but is there a gravitational interpretation of the phase transition? I mean, what happens with it? Is there an intuitive way to? And if so, is there any way to think about it about whether it might happen or not in higher dimensions?
Yeah, about higher dimensions, I'm not sure because this whole story becomes untractable. As soon as you go to d = 3, the matrix model side becomes something more complicated, and I know
that the matrix model side is not going to carry on, at least not so simply, but I mean, if there is an intuitive way to think about the transition from the gravity from the geometric side, then maybe, I mean, that's the main part of the question.
Yes, yes. So let me try to answer that. So I have a slide about that. So one thing you can try to do is to consider the same partition function, okay, and try to solve it using the semi-classical approximation, right? So what you do is, you evaluate the exponential of the action on shell on the 2D black hole solutions, okay? And what you find is, this is in the paper, I think it's section 3.1 or something like that, is that if you construct the t=0 black hole solutions, you see that there is also a phase transition of the black hole solution. This is to say, there is a value of lambda critical for which one saddle point of the equations, one saddle point, sorry. There is a value of lambda critical for which you have two saddle points, two different black hole solutions, okay, that have 0 temperature. And as you go from lambda equals 0 to some lambda critical, there is an exchange of those saddles so that the vacuum energy gets a shift. So this seems to be a way in which
But what are the two saddles? I mean, geometrically, is there any?
Yeah, there are two black hole solutions. Two metrics.
Okay, different sizes, for example.
Yes, they have a different horizon. Yes, the radius of horizon is different.
Okay, it's like a small to large black hole Perturbative transition. Because there are, I think that exists in the literature.
Yeah. It is certainly not new. I agree. Yeah. Yeah, but well,
I'm not arguing about whether it's new or not. I was just, I mean, if you have a nice interpretation like going from small to large black holes, then that's the way to start thinking about it in higher dimensions, maybe.
Yes, that might be the case.
Okay, thanks.
I have a question. Can I ask?
Okay, I have to decide with.
Sorry. That's
Alan
wrong before
and
me.
Carlos. Alan and Carlos. Okay.
There was
question for all of you.
there was a question in the chat before me, actually.
I'm sorry. I hate chats. So who is Danilo? Do you want me? You don't have a microphone, I can tell. In the partition function,
no,
are there? Okay. So I don't know.
Yeah. So the question is whether in the partition function you should also include disconnected contributions, and the answer is no. When you consider more than one boundary, this is to say when you consider two boundaries, you can actually include disconnected contributions, and this map to disconnected correlators in the matrix model. I have never thought of disconnected contributions for a single boundary. So in the case of a single boundary, yes, I wouldn't know how to do the computation from the matrix model side. And from the gravitational side, maybe it has to do with this baby universe stuff that these people, Madoff and Maxwell, have been working on, but to be honest, I don't know. But for more than one correlators, yes, you can include them.
Okay, Alan?
Can you say something very quickly about the non-perturbative corrections?
Yes. Yes. So there's actually an old story on this. So what ends up happening is that for this Hermitian random matrix model, if you start computing non-perturbative corrections, note that say non-perturbative corrections might seem like very high-end stuff, but it's not. I mean, all I'm saying when I'm talking about non-perturbative corrections, it means taking the string equation. Notice that in this case, I'm considering these polynomials that appear over here, that they are a complicated function of u. We have u over here, but then we have contribution from derivatives and so on. This means non-perturbative corrections means solving this differential equation, not by writing a perturbative series for u of x, but directly solving it. And you can do this numerically. So there are two things to have in mind. First, if you do that for this string equation, you find that the non-perturbative solutions to these equations are always bad behavior. This is to say, they have poles or they become imaginary and so on. And this is something that was well known in the 90s when this kind of things was first discovered. And what ends up happening is that the non-perturbative behavior of the Hermitian random matrix model is unstable. Okay, so that's the first thing to have in mind. The second thing is, if we want to solve it non-perturbatively, we have to consider a non-perturbative completion. And that is one of the things that was done in an earlier paper by Clifford Johnson. And this is the same thing that we do in this paper. We actually have to extend that non-perturbative definition so that we can solve the differential equation and get sensible answers. Hopefully that was, it's an interesting, it is an interesting thing.
Okay, Carlos.
No, in the interest of time, let me keep both of the questions. They were follow-up of what Nico Kowalski asked for the discussion. Okay. Maybe let's move. Was a very nice
Perdón,
topic.
pero we know
no,
how
okay.